Welcome to Easy BTech, your guide for BTech and beyond. In the today's topic, we will discuss regarding the transistor biasing, how the transistor biasing are used in the electronic circuits, and for an faithful operation and distortion free output, this biasing plays a very important role. This biasing has been classified into different kinds. That all we will discuss. Okay, students, very important topic, you just go through this. Okay, students, we will discuss transistor biasing. Transistor biasing. Okay. Importance of biasing is to get a faithful output of an amplifier. To get a faithful output of an amplifier. Next, to get a distortion free output. Distortion free output. Biasing plays a very vital role. Okay. Now, depending upon this biasing has been classified into different kinds. The first one is fixed bias. Second one is base collector feedback bias. Third one, self bias. Okay, these are the biasing. As biasing is made, the operating point will be placed exactly at the center. As the operating point is at the center, the output is the output waveform is a distortion free, and it is an excellent amplifier. And using this biasing, we can find a stability factor. Okay, these are the three kinds of biasing techniques. One is a fixed bias, second one a base to collector feedback bias, and third one is a self bias. Okay, students, now we will see importance of biasing. Importance of biasing is to find the stability factor. Okay, for these three biasing, we will find out the stability factor. In the previous session, we have clearly studied what is the stability factor. Stability factor is 1 plus beta by 1 minus beta dou IB by dou IC. Okay. For every circuit, we can find first IB, and we can differentiate IB with respect to the IC. Okay. In every circuit, we can find the equation IB, base current, and we can differentiate with respect to the IC. We will get this parameter. By substituting that, we will find out the stability factor. Okay, what is the stability factor? Stability factor is nothing but change in IC with respect to the IC naught. It means output collector current. Suppose it is a common emitter configuration. For a common emitter configuration, you can see here the base is an input, collector is an output terminal. For that, the output current is IC, output terminal is a collector, and the output current is also IC. To get a distortion free output, that is an IC. Now, what happens? How the IC will change? Now, we know that IC equation, IC is equal to beta IB plus 1 plus beta IC naught. This already we know that from the previous lectures, we have studied all these things. Okay, it means change in IC current with respect to the IC naught as the temperature increases. For every 10 degree rise in temperature, the reverse saturation current will be double. This IC naught is a reverse saturation current, leakage current or minority current. That means because the BJT is a bipolar device, temperature affected the minority charge carriers. Now you can use the FET. In an FET, you don't have the thermal runaway problem or a temperature effect, but a BJT is a temperature sensitive element. BJT is a temperature sensitive element. That is why as the temperature increases, it will show a major impact on the output current. This all we have studied clearly, ma. That is for every 10 degree rise in temperature, reverse saturation current will be double. For every 1 degree rise in temperature, the reverse saturation current increases by 7%. For every 1 degree rise in temperature, the cut-in voltage will decreases by minus 2.5 millivolts. These are the factors. It means the stability factor we can differentiate, that is change in IC with respect to the beta, change in IC with respect to the VBE means IB, and change in IC with respect to the reverse saturation current IC naught. This will affect. That is why to find out the biasing, the stability factor plays a very important role. Okay, students, and for the different kinds of circuits, we will find out this stability factor. Okay, students, we just go through it. The first is fixed bias circuit. Fixed bias circuit. The circuit for fixed bias is it is emitter, it is a base terminal, it is a collector terminal, it is RC, VCC, Okay, students, it is a fixed bias circuit. This is a fixed common emitter based fixed bias circuit. Fixed bias circuit. In the comparison of configurations of common base, common emitter, common collector, we have studied clearly. Common emitter has both voltage gain and current gain is high. Okay, that is why the common emitter is perfectly preferred as compared to the common base and common collector, because common collector the voltage gain is more, but current gain is less than unity or equal to unity, whereas for the common collector the voltage gain is less than unity. That is why this common based and common collector based are not widely used. Is it clear? Because of their low, for a common base low current gain, for a common collector low voltage gain. Those are the drawbacks, limitations for the configurations, whereas if you choose for the common emitter, it has high current gain and voltage gain. That is why we better use common emitter based circuit only. Okay, students, this is the fixed bias circuit. Now by removing the for an DC analysis, for DC X is equal to 1 by 2 pi of C. For DC frequency 0 means X 1 by 0, that is infinity. What you can say? Resistance infinity, the reactance is infinity. it means it can act as a open circuit. Okay, for a DC supply it will act as a open circuit. Capacitor, the capacitor reactance can act as a open circuit for a DC supply. That is why this circuit can be redrawn for a DC analysis like this by removing the capacitors, or B, or C. Okay, this all every time you have to remember: collector, emitter and base, and this type is NPN. If arrow mark is down, it is an NPN transistor. Here the VCC. By removing the this is for the DC analysis. DC analysis. Now we can write the equation here. What is the equation? Input loop. If then input loop, we may write that is a one loop. By applying the KVL, this is the first loop equation, and this is an output side. This will got second loop. By applying KVL across loop 1, we get that is VCC is equal to we will write it is connecting to the base terminal, IB or B plus the voltage between this base to emitter. This voltage is VBE. VCC is equal to IB RB plus VBE. From this we will obtain the IB value. IB is equal to VCC minus VBE by RB. IB is equal to VCC minus VBE by RB. Okay, we are finding the value of IB here. Similarly, this is from the loop 1. From the loop 2, this is a loop 2, we will write VCC is equal to ICRC plus VCE. ICRC plus VCE. From this, if you want to write IC, we will write IC is equal to VCC minus VCE by RC. This will obtain, these are the two equations. It is an equation 1, it is an equation 2. You will find these are the two types of DC analysis by making this collector, that is capacitor open circuit, this open circuit, and we may obtain this circuit as in this manner, and we will write this expression. This is a fixed bias circuit, Okay. Now what you have to do to find out the stability factor? To find the stability factor, therefore we know that what is the equation for stability factor? 1 plus beta by 1 minus beta dou IB by dou IC. Now this is an expression. Therefore we know that IB is equal to, from the previous expressions we can write IB is equal to VCC minus VBE by RB. VCC minus VBE by RB. If you differentiate IB with respect to the IC, dou IB by dou IC. Now there is no IB term here. There is no IB term. Now there is no IB term, then it means, there is no IC term here. Now VCC is a value, suppose it is a fixed 12 volts. If it is a VBE 0.7, it means this is a constant value. Derivative of a constant is 0. That is why this value is 0. The value is 0. Now what you can obtain from this? Dou IB by dou IB, by substituting this value 0, you will get 1 plus beta by 1 minus beta into 0, that is we can write 1 plus beta. Okay, the stability factor, okay, the stability factor, for fixed bias circuit is 1 plus beta. Now from here you can clearly find that this fixed bias circuit is not stable, because as the beta changes, then the stability factor changes. Is it clear? That is because it totally depends upon stability of the system, stability of that circuit of a fixed bias circuit is depends upon only the factor of beta. Beta will vary from 99 to 255. Now as the value changes, definitely the stability factor will change. Now as the beta will changes, as transistor is replaced by other device, then definitely beta will change. Okay, as beta changes, stability factor changes. As beta changes, the stability factor changes. That is why this fixed bias circuit is not preferred. That's why not preferred means as the value of beta will change, it is not a constant, it is not a stable, because as the value of beta will changes, the stability factor changes. Okay students, this is about a fixed bias circuit. Okay, now we will discuss a small example for this with a problem, by taking a small problem, and we will discuss about how the stability factor is finded for this fixed bias circuit. Okay students, we will take a small example. In a fixed bias circuit, the silicon transistor with beta is 100, if VCC is 6 volts, RC is 3 kilo ohm, RB is 530 kilo ohm. Okay, draw DC load line and determine the operating point, and find what is stability factor. This is the problem. Now students, you can clearly understand, for a fixed bias circuit, the silicon transistor with a beta is 100, and if we see, now what is the given solution, you can clearly write. Now the given value, what he has given, VCC given, VCC is 6 volts, RC given, RC how much, 3 kilo ohm, and RB given, RB how much, 530 kilo ohm, and what we have to find, first you have to find the operating point, and the second one is a DC load line, and third one is a stability factor. This we have to go to find, and he has given the value of beta is 100. Okay, students. Now already we know that the expressions, that is to find out the analysis. Okay, first one is a DC load line. Now to find out the DC load line, the first equation is VCC is equal to IBRB plus VBE. This is the loop 1 equation. In the problems we have clearly studied, you can see here once. This is a loop 1 equation. VCC is equal to IBRB plus VBE. Okay. From this, therefore, IB is equal to that is IC is equal to beta IB. Now to find out that IB is equal to IC by beta, we will get the value of IC. Okay, IB can be founded from the value of IC because the beta value is known. Now from this expression here, you can clearly study for y-axis, the load line, you can see load line. To draw the load line equation, from the second loop, that is VCC is equal to ICRC plus VCE. It is a second loop equation. Now for an y-axis, now you can clearly see here. Now you can see this is IC, this is VCE. Okay. Now you can clearly see on y-axis VCE is 0. Okay, for finding IC, VCE is 0. Then we will write the equation VCC is equal to IC RC. From this, to find out the IC value, that is VCC by RC. VCC how much? 6 volts. RC how much? RC in the given problem, in the previous you can say, RC how much? 3 kilo ohm. 3 kilo ohm. Now 3 ones, 3 twos. Kilo will go up. It will become 2 milliamperes. Is it clear? Now on you can see here the value, this is 2 milliampere, the current IC value. IC is equal to VCC by RC. This value you got on the y-axis. Similarly on the x-axis, from this loop equation, IC is 0. Okay, by making the IC 0, what you will get? VCC is equal to VCE, that is 6 volts. That is, you will get directly at 6 volts. This you are getting 6 volts. Now you can draw the load line. Okay, this we will call as a load line. Okay. Now to find out this operating point, now how we can find out this operating point? Okay, to find out this operating point must be exactly at the center. That we will take at the point very clear. That is, we know that IC is equal to beta into IB. Now we know the value of beta, beta is 100, and IB, to find out the value of IB is equal to, in the previous expressions, here you can clearly see IB is equal to VCC minus VBE by RB, VCC minus VBE by RB. Now from these expressions you can clearly find the value of IC. IB is equal to VCC minus VBE by RB. Now you will get IB. IB is equal to how much? VCC. VCC how much? That is 6 volts. 6 minus VBE. VBE 0.7. 0.7 by RB. RB is 530. You can see here clearly. What is the value of RB? RB given 530 kilo ohm. 530 kilo ohm. You can write 530 kilo ohm. Now you can, by substituting this value, you will get the value of IB. IB how much you are going to get? Now 6 minus 0.5. You will get like approximately 5.3. 5.3 by 530 into 10 power minus 3. Now this 0. Okay, this sum, the solution here. If you remove this point here, 5.53 by 530 into 10 power minus 4 of this and 1 by 10. Then approximately you will get 10 power minus 5. This is the value of IB. Now you will get IC is equal to 100 into 10 power minus 5. You are getting that 100 into 10 power minus, you will get 10 power minus 3. Now 10 power minus 3 is 1 milliamps. Okay. Now you are got the value of ICQ. ICQ value is, we are getting here, this is 1 milliampere. And another we can get the value, that is VCC. From these expressions we will find the value of VCE. VCE is equal to VCC minus ICRC. Now VCC how much? 6 minus IC. IC how much? You are getting now 1 milli. 1 into 10 power minus 3 into RC. What is the value of RC? 530. 530 into RC, 10 power 3. RC 530 into 10 power 3 kilo ohm. Now this you will get 10 power minus 3, 10 power plus 3 will get cancelled, and you will get the value of VCE. This VCE value is you will get approximately 3 volts. You are getting 3 volts. Okay, that should be here. Okay, students, you can see from here the what is the equation. This is the equation to find out the VC value. Just you can change, that is VCC minus ICRC. VCC 6 volts minus IC, you are getting 1 into 10 power minus 3 into RC. RC value how much he has given? RC has given 3 kilo ohm. Now substitute here. You get 3 into 10 power 3. 10 power 3, 10 power minus 3 gone. You will get 6 minus 3, that is 3 volts. You are getting the 3 volts, that is the value of this point. This is a 3 volts. Now you can draw the point, this point, this value is operating point 1 milliampere comma 3 volts. 1 milliampere 3 volts is the Q point, and the stability factor, you can find the stability factor. Stability factor is equal to 1 plus beta by 1 minus beta dou IB by dou IC, dIB by dou, this value is 0. Then we will get the stability factor for fixed bias is 1 plus beta, that is 1 plus 100, that is 101. This is the stability factor for the fixed bias. Okay students, easy BTech guide for BTech and beyond.